everyone. I'm Ting Xingling from National Yangming Jiao Tong University. And my paper 有点，不过这个有点难，那个OK， 不然用这个。And my paper title is Neo-Schifate Standard Cell Library Synthesis with PIN-S Optimization on M0 layer. And in the introduction, I will introduce standard cell synthesis and problems to solve in Neo-Schifate cell synthesis. Standard cell synthesis is to physically arrange transistors and connect signals with non-overlapping wires to form a logic gate. This is diffusion, and this is gate. This is contact, and this is M0 wire. This is VR0, and this is M1 wire. The algorithm includes transistor placement and routing. In this page, I will introduce problems to solve in Neo-Schifate cell synthesis. In Neo-Schifate, horizontal routing track reduces, which limits the routing resources. M0 and M1 layer can be used in block level routing. Therefore, the routing grid needs to be redesigned. And metal 2 track coordinates in a row are unknown during cell synthesis. And the M2 track usage is forbidden in our work when synthesizing cells. And a cell has to be multi-row if it is unroutable in a single row structure. This is a double row cell layout. And I/O pins could be allocated on both M0 and M1 layers. This is M1 pin, and that is M0 pin. Currently, there's no algorithm to allocate I/O pins on M0 layer, and we generate M0 pins in this work. And in the preliminary, I will introduce Neo-Schifate structure, transistor placement, and transistor routing. In Neo-Schifate structure, LTC is attached to the diffusion, and LTC connects to M0 and power ground rail through LTC to M0 and VBPR, and the gate connects through M0 to PTC to M0. And in this work, we perform transistor placement following 4 steps. The algorithm is from this paper. First, we cluster devices using common signals in P and N-type devices. And then we pair P and N-type devices with same gate signal. Third, we chain transistor pairs to form partial placement. And finally, we permute chains to find optimized final placement. And as for multi-row placement, we allocate transistors into N rows using FM algorithm and perform transistor placement algorithm on each row. The final result is obtained by exhaustively combining placements from each row and minimize weighted HPWL. And our routing algorithm is from this paper. We first decompose each multi-pinate into 2 pinates, and we then route every 2 pinates with SMT solver in connection graphs. And the result of connection graphs will be copied to the physical graphs concurrently during routing. Then our synthesis flow. We start from the single row structure and we rank our placement candidates. We then check current candidates' routability. If the check-in succeeds, we then apply routing. Otherwise, we switch to the next candidate. If the routing succeeds, the flow goes to post-optimization. Otherwise, we switch to the next candidate. If we have no remaining candidates, we add one row and partition transistors. Then the flow starts from the beginning. And in the algorithm, I will introduce grid graph formulation, virtual node, and our pin overlap reduction. In our grid graph formulation, these are grid points. And we propose a diffusion column M1 only grid graph. M1 can only be generated on diffusion columns. The reason for diffusion column only M1 grid graph is the M1 usage in block level routing. Cross-row M1s on diffusion column and get column will easily cause space violations. In this figure, A signal has a space violation with B. Then I will introduce our concept of M0 pin allocation. Standard cells may be accessed from different regions or directions, and we simulate potential pin access patterns during routing and extract M0 pins from those patterns. The two figures show different pin access patterns in block level routing for a standard cell. Then I will introduce our concept of virtual nodes. These are virtual nodes and virtual edges. We allocate virtual nodes around the cell. For horizontal, one for each row on the left and right. For vertical, we divide horizontal span of the cell into number of column divide number of IO pin regions and allocate a virtual new node to each region on top and bottom of the cell. We also connect virtual nodes to corresponding track and columns with virtual edges in each region. And during routing, we concurrently route each virtual node to I/O contacts. After routing, we remove routes starting from virtual nodes until the last M0 connecting to the diffusion of an I/O signal with DFS and set the remaining M0 as an I/O pin. In our concurrent software constraints, we maximize the number of successful connections to virtual nodes, and each I/O signal had at least one successful connection to virtual node. In this page, I will introduce the motivation behind our pin overlap reduction. Vertically overlapped horizontal pins may easily lead to desirable violations in pin access. Therefore, we reduce the pin overlap reduction. First, we create an access potential vector and we call it AP. The ith element corresponds to the possibility that ith diffusion column is used in pin access. For I/O signal I, we update one divide pin length of I to APJ. J is a diffusion column covered by pins of signal I. And we set a soft constraint limiting APJ must be lower than cap J for all column J. This is cap J. And this is M1 length in column J. And this is M0 routing track. The figure is an illegal case. And this is a legal case. Okay. Then experimental results. We compare our cell synthesis results with this paper. This is cell types and number of contact polypitch, CPP, and the number of rows. And this is our run times. In terms of number of CPP, we improve 1, 1, 2, 1, 2, 4 CPPs in and 2x1 and 2x2 and 2x4, DFF x2 for Adder. And we improve 2 and 1111 CPP in MUX X1 and a series of our cells. Then cells with different number of rows, we improve 264233 CPPs in LY222 Health Aider, MUX X2, OLI222, XNOR2, XOR2. And we also save one row in these cells, and this is our runtime. And in block level PNR, experiments of both works are conducted under core utilization being 70. On average, we save 3.2, 97.6, and 16.5% in area, design rule violation, and wire length among these designs on average. And under the same chip area, we save 97.5 and 15.1% in design rule violation and wire length on the average among these designs. Then conclusions. This is a standard cell synthesis framework for nail-sheet structure. We optimize pin assays, pin accessibility by using two approaches: virtual nodes to allocate out pins on M0 layer, and a pin overlap reduction technique to further reduce conflicts in pin assays. In block level PNR, we improve area by 3.2%, design rule violation counts by 97.6, and wire length by 16.5 compared to a handicraft cell library. Thank you.
Yeah, thanks for the speaker. Is there any questions? Okay, I have a question. It looks like previously there are some work can be like configured in this kind of like nanosheet, for example, the CFA-based routing from CK-Chan's group. Do you consider to compare with them?
But the cell structure is not the same, so we do not compare with the CFA cell library.
Actually, they have SF7, and then it's very easy to change to this.
Change
for
setting.
SF7. Yeah. Maybe you can consider to compare with them in the future.
Oh, thank you.
And okay, so I have another question. So for virtual pin, usually one cell have multiple like pins, right? And then for virtual pin, did you consider the interaction between two different external pin access? Because sometimes when one pin access one access point and the other pin can actually not be accessed some pin opening because the design rule. For example, let's take an example like NAND2, right? NAND2, you usually have A1, A2 plus Y. So you have 3 virtual pins. And then, so here, you only consider, for example, one virtual pin and connect to whether it can connect to the, like, one of the pin. But my question is whether you consider the interaction between different pin access, their interaction between, like, for example, A1 need to access one pin, and A2 also need to access the other pin, and then they.
But this work in
Yeah, it's like this, like a pin access region. You have the virtual node, right? The virtual node, it's only one net, or it's like a multiple net, for multiple external nets. Okay, that's okay. Yeah, and okay, if there's no more questions, we can discuss offline. Yeah. Okay. Thanks, speaker again.